Now let me ask you, are there any traders in the room? Any traders? Okay, a couple traders. Those of you who aren't raising your hands, what are you guys doing with your free time? So the next session is going to talk about the struggles of trading. In a world of endless chains and scattered liquidity, users often face the impossible task of choosing the right risk, route, and timing for every trade. Our next speaker and his protocol are trying to solve that. Please welcome to the stage Alex Vinas from CoW.
Thank you. Welcome everyone. Buenas tardes. Thank you for taking the time of your busy day to be here and listen to what I have to say. And thank you to the EF for allowing us the opportunity to speak in this wonderful event. And today I'm going to talk about what is CoW's current approach to multi-party execution, and also what is CoW's approach to the whole cross-chain coordination game. I'm Alex Vinas. I'm the head of partnerships at CoW. I've been with the team since the beginning, since the spin-off, so 5 years ago. And before, I actually worked in the back then so evil TradFi, but now kind of cool because they're coming on chain. So I've broken down the talk into 3 main topics, which is going over why actually cross-chain coordination is a hard problem to solve, to then go into CoW's handling of multi-party execution, and then to finish off with what we're actually building to go cross-chain in terms of how we coordinate the whole intent cross-chain auctions. Oh, sorry. So the cross-chain wall, right? The cross-chain is very hard, mainly because of 3 problems. Because first, the amount of chains there are. There's been like an explosion of chains throughout the past years. And also because of the amount of choices that the users have to make to actually make a secure transaction and know what they're actually doing. Then you also have the whole problem of no execution atomicity across chain, that this is something that kind of breaks everything within the smart contracts, because if you live in a single chain world, then you have execution atomicity, but if you go cross-chain, then you suddenly lose this. And lastly, you have the whole like chain reorg problem, that while in Ethereum hasn't happened, in many other L2s, this is more of an issue these days. So endless choices, right? If you're a user, you have an abundance of chains to go, and also an abundance of ways in which to go to these chains. The problem is that if you're a normal user, you probably don't have the time to do all the research and actually evaluate all the trade-offs of, okay, is it better for me to use a native bridge? Is it better for me to use a bridge aggregator? Or is it better for me to actually use Coinbase or Binance to simply bridge the assets? Not only that, but from the point of view of the chains, you have the different trade-offs that these chains provide, like how long do they take to provide me finality? What stage are they on in terms of like the decentralization? Or most important, like what happens if I want to move my funds back to the main chains? So from the user point of view, it's kind of very hard because you need to do a lot of research to figure it out. And this is the problem that has not been solved, and at CoW we're kind of like trying to tackle this. Then the second problem we have is that you don't actually have execution atomicity, right? And this is kind of the biggest problems of the cross-chain world, because if you live in a single chain world, then if we look at this, for example, right, and if we look at this, for example, and we see the simplest kind of settlement contract where you have a sell token and a buy token transaction, the beauty of this and smart contracts, what brought the difference kind of like of TradFi, is that you don't have counterparty risk from the point of view of the infrastructure, right? The transaction is atomic. I will only release the buy tokens if the sell tokens have been given to me. Now, however, the moment you move cross-chain or the moment you move multi-chain, this atomicity is not guaranteed by the chains themselves, but rather by third parties, right? So we have oracles or different providers like Layer 0 or Wormhome who have different messaging systems that actually communicate between chains to actually tell you when to release the sell token. However, even though this reduces a little bit the counterparty risk in terms of cross-chains, you're still relying on single point of failure, and you basically can end up in a scenario where you're releasing the buy tokens, but then in reality, the sell tokens in the origin chain hasn't actually been moved yet. So this is a problem because then from the point of view of the kind of exchange or the swap provider, you would have given the users the output token, but you haven't withdrawn the sell token. So you end up losing because you haven't kind of charged the tokens that the user wanted to dump, and you have given them actually like more money. So you've made a user happy. And then the other big problem that you have that luckily in Ethereum it doesn't happen, but in other kind of layer 2s or adjacent chains that move around Ethereum it does happen, is the whole reorg problem, right? Because validators are geographically distributed across the world. They need to figure it out a way into which come to consensus. And this actually means that temporarily they might see a different version of the chain. And now, how does blockchain come into consensus? Well, they define what is the fork choice rule, which in the case of Bitcoin is the chain that has the most amount of proof of work, is the chain that is valid and the one that like the transactions you have to trust. And in the case of Ethereum, no, in the case of proof of stake, it's actually the chain that has the most amount of attestations. And that's the chains that valid and the transactions that are going to be counted as finalized. Now, additionally, in proof of stake chains, you also have the concept of finality, which is finality guarantees because you have these checkpoints that basically the whole idea is that every 64 blocks in Ethereum, so every 2 epochs, no, we kind of consider the transactions finalized and 100% confirmed. And this means that those transactions can no longer reorg. I mean, here, like a small kind of point is that if kind of the community decided to soft fork or hard fork, you can still reorg. But from the point of view of the checkpoints, like in terms of like if there's a fork choice from now on, then that means that those transactions can no longer be reorganized. Now, the problem that also comes with reorgs is that even though the transaction is confirmed once it lands in a block, you still have to wait for finality. And this is a problem because the moment we actually have like a fork choice, right, or a reorg kind of in Ethereum, this means that transactions can be completely different, right? So if we look at an example where, let's say, like we have a fork choice, and now because whatever kind of issue within one client, kind of 20% of the network is going on the top chain, and 80% of the other network that doesn't have that bug on their node is actually validated on the chain below, right? So in this case, the canonical chain, the one that has the most attestations, is the chain below, and the one that is on the top is actually like what there's called like the uncle blocks, and the ones that's discarded. Now, this is the problem because if you have mutually exclusive transactions, right, your history is completely different. Because if the first chain, if what's now the uncle chain, would have won, that means that kind of Bob would have deposited ETH in the bridge and could have not sent ETH to Alice. But because the chain that won was the canonical chain, the one below, actually the first transaction that happened was sent ETH to both. So this is kind of problematic because, right, if you've done like a swap, but then there's a reorg and the swap kind of reverts, you might end up in a scenario where kind of the user has like a on-check balance and they have the tokens that they didn't ask, or they couldn't even, or you as the exchange kind of withdraw the tokens themselves. Now, I'm going to give an overview of basically CoW's approach to multi-party coordination and how we kind of upgraded our old model from simple frequent batch actions to actually like multi-party execution via combinatorial batch actions. And in case you didn't know, and I don't know, you haven't heard the famous Moo, CoW is kind of the inventor of the intents. We were the first project to do intents back when it wasn't cool, when it wasn't a fancy word or a buzzword. And this was 5 years ago. And the whole idea was basically to build with these 3 premises, where if you combine intents with frequent batch actions and solvers, you could give the user a much better execution than the common or average kind of DEX or DEX aggregator that back in the day we had. So first, right, the main buzzword or the main kind of thing that drives the OEF and all these conferences today is intent. So what is an intent, right? An intent is simply an expression of I want to trade A for B, and I allow you to do it on my behalf. Now, based on this, the big difference, right, is that the user is, instead of signing a specific call data or a specific path to tell the solver or tell the DEX, hey, I want to swap in these specific pools, you're rather saying, I want to swap these quantities, and as long as you respect my limit price, I don't mind where you do it, and I don't mind how you like distribute or chop my trade. Now, intents combined with frequent batch auctions are very powerful because you can actually like achieve guarantees that other ways you couldn't. So for example, like if you're doing intents, then you're shifting the whole MEV exposure that the user has to the solver, and then the solver is the one that has to figure out how to do MEV protection. On top of that, you actually can do coincidence of ones, which is actually how the whole name of CoW came to be, which is a powerful quality that only CoW has, which is the idea to match counterparties together instead of matching them with external liquidity pools. So in a sense, if someone is selling ETH and another person is buying ETH, why depend on external liquidity when their liquidity can completely overlap? Not only that, but it also actually, the fact that you're using batch auction, it allows you to aggregate like multiple transactions in a row and also define a clearing price for the same token pairs that are trading against different points in time. And lastly, you delegate the execution of these intents to solvers who are professional third parties that know way better because their job is to actually optimize these transactions than you as a user. So these solvers are teams that can actually tap into private liquidity, on-chain liquidity, or even their own private inventory to kind of provide the best price for the user. So from the point of view of CoW, when we run an auction, it doesn't matter where the liquidity comes from, as long as the user is guaranteed that they get the best price. So we've seen multiple combinations where, I don't know, 20% of the trade will be split with on-chain liquidity, 20% will be done with a market maker, and then maybe 60% is actually done via the coincidence of ones with other users within the batch itself. So now our old batch auction mechanism, our old model, the whole idea was, okay, we have different users from either CoW interface or different interfaces that actually sign their intents, which basically creates the orders, and then these orders are registered on the order book. Now, once the orders are in the order book, we actually execute a big batch auctions where solvers have to compete to provide the biggest price improvement, the biggest surplus to the users. And the solver that provides the biggest amount of total surplus for the users within the auction is the solver that won the right to settle the execution. Now, this is a little bit abstract, so maybe with an example, it will be way easier, right? So if we look at these for users and these for swaps, we might have, okay, Emily wants to swap stake ETH for USDC. Then Edith wants to swap USDC for wrapped stake ETH, which actually in here is the powerful example of a coincidence of words, where the USDC can actually be fully overlapped between the users and we don't need external liquidity. Then we have Chao that wants to swap 1 each for CoW tokens. And then we also have Rene who wants to swap Aave stake ETH for Aave tokens themselves. So the way the solvers will work is that now the auction has begun and they have to place the bids. And for example, we have, okay, solver A is going to bid on orders 1, 2, and 3. So the stake ETH 1, USDC, wrapped stake ETH, and 1 each in CoW. Solver B is going to bid on orders 1, 2, 3 as well. So they're in direct competition. And then solver C is only going to bid on order 4. Now the old results, right, in the traditional batch auction model would be that, okay, solver A is the best bid on the total amount of surplus in the batch because he's a specialized solver and he has been able to create a coincidence of one. And because coincidence of ones are the ones that create the biggest price improvement instead of tapping into external liquidity, he's the one that has created the most amount of total surplus for the orders in this batch. Then we have solver B, who unfortunately, their algorithm is not capable of doing coincidence of one, so instead it uses AMM liquidity to solve orders 1 and 2 and 3, but the difference between the bid of solver B and solver A is that actually in the solver B created way more surplus on order 3 than solver 1. And then lastly, we have solver C that actually did the best bid, but it only bid for order 4. Now, the result of this is that only solver A is going to win. Solver B gets completely ignored because the total amount of surplus it's less than the actual solver B. And then solver C is, the solution is completely ignored because you have the single winner constraint, right? The whole idea back then is that we can only have one solver executing the result of an action at a time. And of course, while this worked, it had some problems because we actually missed a better execution route, right? In the case of solver A, the user for order 3 was executed with lower surplus that someone else actually found on chain. It also means that we executed with lower throughput because instead of CoW having executed 4 orders, we only executed 3 orders. And then something that I guess maybe many people didn't know is the fact that we also had to do a post-auction fairness check with what we call the Ethereum best bid offer logic, because then we would have to make sure that actually solver A provided the best available bid for the third swap in a row. And in the case that they didn't, then they could get penalized and they would earn less rewards. Now, in the new model, the way that we do like multi-party execution is through combinatorial auctions. So if we have the same system, now the big difference that instead of kind of auctioning on the whole thing and solvers having to bid on the entirety of the auctions, now actually solvers can only bid on certain parts of the auctions. And this means that now solvers can actually specialize on only like certain token pairs or certain specific routes where they know they can really outcompete other solvers. So if we go back to our example, right, where we have the 4 ways to swap, and it's the same like stake ETH to USDC, we will have the same bids where solver A is bidding to orders 1 to 3, solver B 1 to 3, and solver C is only bidding on order 4. Then the results with combinatorial auctions are actually completely different. Because then solver B is going to win with the best bids on order 1 and 2. Solver B is going to win because it has the best bid only on order 3. It's the order that actually individually has more surplus. And then also solver C is going to win because they have the best bid on order 4. So the big difference is that now we have achieved a higher total of surplus within the batch by executing individually these type of trades instead of like all together in one auction, which means that now CoW has more higher throughput. We can execute way more orders at once than before. And actually, like, it saves us a lot of time and a lot of kind of engineering hours because we don't have to dedicate the time to doing these post-facto fairness checks of Ethereum best bid offers from solvers, because now the fairness is encoded in the mechanism, right? We're gonna allow the solver to execute that has the most amount of surplus on single orders. There's no kind of collusion like there was before. Okay. Now that we've done kind of how we do on, let's say, single chain multi-party execution, let's see how we do the cross-chain coordination in this multi-party execution environment, right? So if we have, I guess, if we continue with the examples of users are placing intents within the different trading interfaces, then the way we actually do cross-chain is that we do the swap on the source chain. So basically, like, the first thing is that we separate the swap and the bridge intent, and basically the swap has on the source chains that the users want to trade. We do, let's say, ETH to USDC or Arbitrum to ETH in the main chain, and then we actually call what we call swap and bridge. We call bridge aggregators to then bridge the output to the target chain that the user has defined. Now, another variant flow that is not live yet, but we're working on it, is the whole idea of doing bridge and swap, and bridge if you want. So why is this important? Because, for example, right, depending on the chain you're in, the depth of the liquidity and the type of trade that you want to execute might be very bad. Now, however, maybe this is not the case for the same token pairs on Ethereum or on another chain, which with this, you can actually do, okay, let me first bridge my asset to the chain that has like much more like deeper liquidity, execute the swap there, and then actually like bridge back the proceeds to the chain that I want the tokens to be in. But because this is not live, let's just focus first on the swap and bridge, which is what already currently live today. So if we go through an example, right, as I say, our current way to do cross-chain coordination is basically to split the swap intent with the bridge intent. So if we say I want to sell 100 ARB tokens that are living on Arbitrum for 1 WETH on Ethereum, what would happen is that the intent gets registered on the order book, and basically solvers compete to sell 100 ARB tokens for 1 WETH within Arbitrum. And as I said, the solver that provides the most amount of surplus for the user is the one that actually gets to execute the order. So once this has happened with something that we call a post hook, instead of giving the funds back to the user, we actually send the funds back to this kind of smart contract that we've called the CoW, which is sort of a flavor of account abstraction because the user doesn't have to trigger anything or do anything with the contract. It's also unique per user account, so the user EOAs fully controls the deployment of this CoW. And then the interesting part is that via ERC 1271 signatures, actually the solvers as the one that called the contract and say, okay, now actually bridge via this mechanism that CoW told me is this bridge aggregator that CoW told me is the best way to bridge my assets to this other chain. And the whole idea of doing it via the contracts is because then the solvers are the one that can actually execute this call. Because from the point of view of the cowshed, the cowshed will validate, okay, I have the funds from these users, and now I know that I need to transfer them to a specific chain as long as this kind of call data that someone is passing me is what's encoded within my logic. And now this is what the solvers do, that once the kind of swap has happened, or once the solver has the one WETH, it actually calls the contract and say, I'm bridging these assets on behalf of the other user. And then, of course, once the bridge has already, the bridge aggregator, there's a winner, has been selected, the user enjoys the tokens in the destination chain. Okay, now that we've covered more or less the problems and CoW approach to multi-party execution and kind of our current flavor of cross-chain, I'm going to explain what we're working on for cross-chain auctions and cross-chain intents before, it was this fancy word. Now, one thing to take into consideration is that intent is a very easy thrown word. And there are certain limitations, because as we saw in the first slide, there are endless choices from the user from the point of view of chains, but not only that, from the point of view of speed, security, or fees, right? How do you really encode the fact that a user says, I don't know, I'm 50% okay with if I'm way faster and I pay a higher fee, but I'm 20%, okay if I do it the other way around, right? It's really hard to encode everything in an intent. So from our point of view, the simpler the intent, the easier the life of kind of the auction mechanisms that handle intents. So for our cross-chain coordination, right, what are our requirements that we have? As mentioned, because there's so many trade-offs between speed, security, and fees, we actually want to unify this user choice around one single kind of category, and this category is what kind of CoW is going to deem trustworthy, or kind of what's going to be considered okay to do the trade-offs for the user. The second one is that we want to actually do true cross-chain intents to improve the UX, right? They should be okay, sell X on chain A for sell Y on chain B, instead of the current swap and bridge flow, where you actually, even if you approve, you have kind of 3 steps. You have the approval, you have the swap, and you have the bridge. But if you have done the approval before, you only have 2, right? It will be the swap and the bridge. So the user experience needs to improve, and it needs to be a single transaction and a single click, like swap A in chain A for B on chain B. Then the other important point that no one talks about is that it needs to be capital efficient, because we need to reduce the solver barrier to entry, right? All these other solutions basically are very capital intensive, and kind of no one is talking about it, because if you're a solver and you want to solve for $100,000 trades across 10 chains, that means that you need $10 million of private inventory. And this is problematic because not all of 10 entities have $10 million in their pocket to actually do market maker cross-chain. And it's even more problematic for the user, because that means that there's way less solver competition, which leads to getting worse prices, right? But this is why, for us, capital efficiency is a very big point. Because one of the aspects that we learned from Gnosis Protocol V1, which is kind of the precursor of CoW, is that the systems need to be compatible with permissionless liquidity as much as possible, because in the event that there is no one kind of market making, the ability to tap into liquidity pools like Uniswap, Curve, or Balancer is actually way beneficial, because then you can actually do the execution per se. And then lastly, it's also enabled to do capital efficiency, right? You want to allow coincidence of ones, right? Why do a complicated mechanism or involve a market maker when you have a perfect match between a user that's jumping from one chain and a user that's jumping from another chain? So this is also why we're focusing on improving the capital efficiency in this part. And I guess this one's for the engineers, right? It needs to be easy to add new chains, because if not, it's a pain kind of to do all the work to add a new chains. And one of the things that is important for us is that back in EdCon in 2018, our CTO did this presentation on how actually multidimensional batch auctions help reaggregate fragmented liquidity across the many stablecoins, because back then we saw, okay, there's an explosion of assets, and you have, for example, a lot of stablecoins that represent the same asset, the same underlying asset, right, the dollar, but they're completely fragmented in terms of liquidity. And here's where the kind of multi-dimensional batch auctions come to the rescue, because they help to reaggregate these markets and kind of create a fair clearing price across them. But now, instead of doing it per tokens, we're actually doing it per chains, because now, we have kind of like an asset explosion to the power of chains, because not only you have USDC, DAI, USDT, or whatever other stablecoin, but you also have USDC on ETH, USDC on Base, USDC on Optimism, and so on per network. So this is why we think doubling down on multi-dimensional batch auctions will actually help reaggregate this fragmented liquidity across the chain, and will actually be beneficial for the users. So now that we have the requirement, let's go through the core components, which is basically permissionless and composable liquidity. So the ability, as I said, to tap into the liquidity pools in combinations of a ledger that can actually keep track of what's coming in and what's coming out in terms of user balances. Then the whole idea of account abstraction balances, right? Like if we want to, I guess, move like TradFi, it's $100. It doesn't matter if I have 50 on Base and 50 on ETH, it's $100 in total. So the idea is that with a chain abstraction protocol, the user has the same balance across different chains, and you can actually show a single balance, which means that now the user can kind of be the liquidity provider across chain within the updates of the ledger that you might do. And lastly, you need to have fair combinatorial auctions, because you can't throttle the system where there's only one solver winner all, but rather you have multiple winners at once, so that you have a higher level of throughput. So how it works is basically you have a cross-chain CoW ledger where basically user balances are recorded, and then you combine that with the composable liquidity, right? So for example, we will have a user that has balance on ETH, and then a user that has a balance of 1 ETH, and a user that has balance on Base of 1 ETH. Now, if they were going to do a swap, in this case, I'm going to explain in the next slide, the example is the user one wants to sell the ETH for USDC on Base. Now, the difference is that instead of just relying on a single cross-chain CoW ledger, we also have this deposit contract where users deposit the fund, but they can also play these resting limit orders that will allow for the cross-chain operations to be much more smoother. And then lastly, one big unified auction where you can actually also specify the source and the target chain. Because right now, the way even the combinatorial auction works is that you have kind of the auction per chain. And instead, we're going to be moving to a whole unified auction where if it's only swaps for single, like in the case of combinatorial auctions, right? If the winner is only doing source and target of the same chain, then fantastic, we don't need to do anything cross-chain. But in the event that certain orders are coming from cross-chain where the source and target are different, we can actually handle it in the proper way in the same auction without doing the whole swap and bridge. So let's go through an example to see what these three pieces that I mentioned work, because now if we're running the combinatorial batch auction, we could have a world where solvers, for example, are bidding on orders that are happening only on Arbitrum, orders that are happening from Solana to Bitcoin, or orders that are happening only on Ethereum, or orders that are happening from Ethereum to Base. Now, the important part of this auction is that the results of it need to consist of two important pieces. One is a bunch of cross-chain CoW ledger updates so that we actually keep the track of the balances, and then a one-chain settlement transaction. And I'll explain here why. So in our example, right, we have, you can see, we have user one who has ETH on mainnet and actually wants to get USDC on Base. And then we have user two who has ETH on Base and is one of those users that kind of is activating the account abstraction balances and is placing a resting limit order within the causal deposit contract, telling us, I guess, I don't care where my ETH is as long as it's 1 ETH. As long as you respect my balance, I don't care if you move it cross-chain. Now, we already have a CoW in the sense that we can actually give the ETH from user 1 to the ETH on user 2 and the ETH from user 2 to 1. However, the problem is that user 1 actually didn't want ETH. They wanted USDC. So this is where the on-chain settlement transaction component part comes in, because then a solver can say, okay, well, because this user needs USDC instead of ETH, I'm going to go grab the ETH from the deposit contract, and I'm going to go on-chain to a liquidity pool like Uniswap or Curve or whatever, and I'm actually going to swap. And I'm going to swap 1 ETH for whatever the result in USDC. When I did the slides, the price was higher, but let's say it's 3,600. And the important part is that this solution is actually how you achieve the atomicity across the cross-chain swap, because you make basically the conditional, right, the validators, So in order to co-sign the transaction, for the validator to kind of verify the solution and co-sign the transaction on chain needs to happen. So in other words, right, if the on-chain exception is observed before, then the validators will kind of deem this transaction as approved, and they will actually push it, and kind of the transaction will execute. However, if the execution reverts and you don't have kind of the part of the USDC for WEF, then the execution will revert and you won't have the updates on the ledger. And this is how we kind of see how we do atomicity across chain, because if you combine like ledger updates with the fact that only one on-chain settlement transaction can happen, you can actually guarantee that either kind of the balances move in the correct way and the user's desired outcome has happened, or it will simply revert. And this is what we're building so far, and I'm running out of time, but just in time. So thank you very much for taking the time.
Thank you so much, Alex, and thank you so much for showing the exact steps that people need to take if they want to implement the changes that you're making. I hope that this was very informative for